Take 2 now. Assalamualaikum and hi everyone. My name is Muhamad Arash Hakim. I am final year student and this video is about my final year project. It is about the application of Gen 4 for the efficiency calculation of alpha particle with nitrogen particle. The title of this project is a bit difficult to understand, but it is not. I'm going to explain it in the simplest way. The idea of the project comes from the fundamental knowledge of nuclear transmutation process. Now, what is nuclear transmutation? Nuclear transmutation is the process that the conversion of the one chemical element or isotope to another chemical element. Since any element or isotope is identified by the number of proton and neutron in its atom, nuclear transmutation may occur in any phase where the number of proton or neutron in nucleus is modified. The transformation may result from the nuclear decay of radioactive isotope or may result from the capture of neutrons. This process involves a change in the element of the atom. When the number of proton in atom is changed, the atom is transmitted into an atom of another element. As you can see from figure show, as the single alpha particle collided with the nitrogen particle, they are forming a compound nuclear reaction. And this compound nuclear reaction is unstable and they must decay to achieve a stable state by emitting a single proton out of the nuclei. Thus, the remaining nuclei are called oxygen particles. The ideas of nitrogen particle being collided with alpha particle were discovered by Rutherford in 1919, and this is the birth of nuclear transmutation process. In real-life experiment, artificial transmutation may occur in machinery that has enough energy to cause change in the nuclear structure of the element. Such machine is called particle accelerator at CERN in Switzerland. The purpose of this project is to study the behavior of nuclear interaction between alpha particle with nitrogen particle without any disturbance of any other gases inside the simulation process. The application of Gen 4 that have been developed by the CERN community that are able to predict the outcome of nuclear reaction efficiently. The main target in this project is to measure the amount of oxygen gases isotope that have been produced and consider the other possible reactions that may occur during the reaction process. Now, how am I going to do it? First, the tools that need to be used are called Linux operating system and several other installment tools such as Gen 4 library package managers and root analysis framework. With the knowledge of the object-oriented programming method and many other examples that have been provided by other software developers, the source code for the project can be reconfigured and reconstructed based on the requirement of this project. Next, in this figure, the chart shows on 4 different categories that need to be reconfigured and adjusted. The first is detector construction. Here, the geometry of the detector need to be constructed and material used for the simulation of the detector need to be defined here. And this is the example of the source code inside the detector construction code. Second is the physical process. The process of collision particle, electromagnetic event, and energy of bombarded particle and type of the bombarded particle need to be constructed in this code. Third is the particle source. This part is important to determine which type of particle will be taken into consideration for collision process. The default type of particle must be considered and set as a default program. Lastly, in order to collect data, it is necessary to visualize data and set up code to calculate all major parameters such as mean free path, cross-section of collision, and total generated particle. And here is some of the demo on how to execute simulation in batch mode. After the simulation process, the result obtained can be seen in this slide. All these figures shows the total amount of stable oxygen gases that have been produced at energy range 1 until 200 MeV. As you can see from the figure A, red line, initially the particle that have been generated from the reaction is oxygen 17, and at 18 MeV the amount of oxygen 17 being produced is at maximum, where the energy transfer is high enough to remove a single proton out of nuclei, but it is not enough to remove neutron out of nuclei. As kinetic energy of the alpha particles start to increase, the total amount of oxygen 70 particles start to decrease as the generation of oxygen 16 particles start to increase. Next, the purple line, the generation of oxygen 16 start to increase as the energy transfer from collision is high enough to remove neutron from the compound of nuclear fluorine. The generation are most likely start to occur when the oxygen 17 start to decrease. The generation of oxygen 16 start to dominate greater than oxygen 17 and oxygen 18. But due to the other possible particles that have been generated by the reaction process, the total amount of particle oxygen 16 that have been produced start to decrease. Also from figure A, it also shows the small number of oxygen 18 that have been generated. The generation of oxygen 18 are most likely to occur only when the alpha particle collided with the nitrogen 15 particles. Figure B shows the total amount of stable isotope that have been produced, range of 40 until 200 MeV. We know from figure A the total amount of oxygen 18 oxygen 16 that have been produced are decreasing, approaching 40 MeV, but from figure B the number of oxygen 16 that have been produced after 4 MeV suddenly peak compared to less than 40 MeV. To explain this situation, it is necessary to see the other possible reaction that occur during the reaction process. We know when the alpha particle collided with the nitrogen 14, it will become a compound nuclear reaction. A compound nuclear may decay in a variety of ways, and the compound nuclear model of nuclear reaction are based on the assumption that the relative likelihood of decay in any particular collection of final product is actually independent of the compound nucleus formation. Now, in order to analyze the other possible reaction, we need to collect data of the other most dominant reaction inside the simulation process. From figure E, when the cross-section per atom start to increase from O to A, the most dominant reaction is oxygen 16. Then, as the cross-section per atom start to decrease from A to B, the reaction of lithium-6 reaction start to dominate the process. The decreasing in cross-section per atom will cause reduction in the oxygen 16 generation. At turning point B, as the cross-section start to increase back again, the generation of oxygen 16 reaction start to increase drastically until it reaches C, where the kinetic energy are high enough for oxygen 16 reaction to be dominant again. It can be assumed that all type of reaction are basically appear at certain cross-section range and kinetic energy of incident projectile. Nevertheless, when the alpha particle collided with nitrogen gas and forming a metastable fluorine, the decay process formed into any final specific state that is nearly independent of how it was originally formed. Lastly, there are other reactions that need to be considered, which is the reaction of carbon 12. It can be assumed that nuclear fission occurs at a nuclear transmutating process. From figure D above, the amount of reactions is increased drastically, more dominant compared to that oxygen 16 and lithium 6 reaction. The next part is the collision behavior of oxygen 70. As you can see, even though the density and the temperature of the reaction is different, this figure shows that the nuclear reaction of oxygen 70 at wide range of oxygen energy 0 until 180 MeV is actually not influenced by the external environment such as density, temperature, respectively. This is proven by the Pierre Curie and M. Kamerlik honors MIT 2018 in 1930. They measured the rate of decay of radium at room temperature and subsequently being cooled in liquid hydrogen, resulting independent of decay rate with respect to temperature. Since then, many experiments have been conducted and it has shown that alpha and beta decay are not influenced by the external conditions such as temperature, air pressure, or the surrounding material. So it can be said that the nuclear transmutation process are not influenced by the external environment factor. Now I'm going to talk about the mean free part. As you can see from all these three figures, it shows the distribution of mean free part by the influence of three different types of external environment, such as temperature, density, and pressure, respectively. For all such cases, similar conversion pattern is observed. In order to understand this pattern, the main free part must be correlated with the kinetic theory of molecules and nuclear reaction cross-section. From this figure, the mean free part of the reaction is decreasing from point A until B. It is due to the increment in the cross-section of nuclear reaction. It is reflecting the low energy of alpha particle to interact with the target nuclei. The Coulombic force between the target nuclei and alpha particle is greater than the energy of incident particle. Thus, the distance between the particle is far from each other will limit the collision process. Initially, at 1 MeV, most of the reaction that occur is only the transportation process, indicating the movement of alpha particle in the box with a very few collisions. The cross-sectional area is defined as the average cross-section per unit molecule, where the greater the total number of collisions between the particles, the smaller the number of section average. In conclusion, simulation for the nuclear transmutation is important for the measurement and characteristic specification of the reaction process. Throughout the project, the reaction of alpha particle with nitrogen gas have many different characteristics and possibility of the reaction. The mass of the constituent element after the collision are difficult to determine as the formation of trajectory particles only occur when the number of alpha particles increases. The average mean free part of the particle and cross-sectional area of the reaction are varied with different kinetic energies of alpha particle. The flux of the detector is directly proportional to the total number of particles per event of the simulation. The ideas of using Gen4 to simulate on how the bombardment of one type of nuclei are able to synthesize many new elements, and it's also able to predict the results that are almost identical with the actual result of the experiment. For future work, the study characteristic behavior of the transuranic element via nuclear transmutation process is recommended. The transuranic element is the chemical element with the atomic number greater than 92, which is the atomic number of uranium. The current project has used alpha particle with nitrogen gas particle. In future work, it is better to understand on how synthesize transuranium nuclide other than using alpha particle with nitrogen particle. Such example is the collision of neutron with the transuranic element. All these elements are unstable and decay relatively into other elements. Thank you.